They power the jets that fly us across continents, and they light up the very cities we live in. Yet most of us have never actually seen one up close. They're kind of the hidden giants of our modern world. So today, we're going to pull back the curtain and find out exactly how a gas turbine works.
Just look at this thing. It's incredible. This machine right here is the core of both a jet engine and a massive power station. And the secret to its insane power, well, it's basically the same for both. We're about to follow the journey of a little bit of air as it goes right through the heart of this beast. You're going to see how it's done.
All right, so this whole incredibly complex process, it really just boils down to 4 simple, powerful words: suck, squeeze, bang, and blow. Now, engineers call this the Brayton cycle, but this is all you need to remember. It's our roadmap. The engine sucks in a massive amount of air, squeezes it like you wouldn't believe, ignites it at a controlled explosion, and then blows that hot gas out to create power. So, let's follow the air.
First up is the squeeze. And believe me, this isn't just one simple step. It's probably the most critical, most energy-hungry part of the whole deal. This is where the real work of the engine actually begins.
Now, check this out. See this section right here? This maze of blades? That's the compressor. It's basically a series of thousands of tiny, super strong wings, all lined up in rows. Each row gives the air a little squeeze, then passes it to the next row, which is a little smaller, and squeezes it even harder, and on it goes.
And what's the result of all that squeezing? Well, the pressure of the air can get jacked up by a factor of 40, sometimes even more. I mean, think about that. The air coming out of that compressor is 40 times denser than the air that went in. That is just a massive amount of potential energy, all stored up in the form of pressure.
Getting this squeeze part right was the absolute key to making gas turbines work. Early attempts, they've failed right here. The turbines they built just couldn't produce enough power to run their own compressors. It just goes to show you how vital and how incredibly difficult this first step really is.
Okay, so now we have this incredibly pressurized air. It's just sitting there, ready to go. So what's next? It's time for the bang. Let's head over to the combustor and see how we light the fuse.
So the combustor is where we turn all that pressure into raw heat and power. And it's not like one big kaboom. No, think of it more like a perfectly engineered continuous blowtorch. Fuel gets sprayed into that super pressurized air and lit, creating this sustained roaring fire that's carefully managed to make a non-stop flow of extremely hot, high-pressure gas.
So we've just created an absolute hurricane of hot gas. Now what? Well, you can't just let all that energy go to waste, right? We need to harvest it, and that is the job of the power turbine. This is the blow stage of our cycle.
And this is probably the most mind-blowing fact about the whole thing. As that hurricane of gas blasts through the turbine, it generates a colossal amount of power. But get this, a full 2/3 of that power is used for just one thing: spinning the compressor back at the front of the engine. The engine uses most of its own power just to keep itself going. Only that last 1/3 is the usable power that actually pushes a jet forward or makes electricity for your home.
So how does that final 1/3 of power actually get used? Well, this is where our one machine splits off to do 2 totally different but equally vital jobs, all using that same core principle.
Okay, so look here. On the left, you've got your jet engine. Its whole purpose in life is maximum thrust. That blow phase is funneled right out the back through a nozzle, pushing the plane forward. Simple. But over on the right, in a power turbine, the goal is totally different. It's designed to capture as much of that energy as possible. It uses extra sets of turbine blades to turn all that hot gas into rotational power, spinning a big shaft that's hooked up to an electrical generator.
As we wrap this up, it's so important to see this machine not just as a few simple steps, but as this breathtaking engineering balancing act. It's constantly running at the absolute edge of what our materials can even handle.
So what's the ultimate challenge for the people who design these things? Well, it's managing a whole set of extreme and often conflicting forces, all at once, inside a machine that's spinning tens of thousands of times a minute.
I mean, they're juggling parts so hot they would literally melt if not for these crazy complex cooling channels built right into the metal. They're trying to manage airflow that moves faster than the speed of sound, creating shock waves inside the engine. They have to deal with immense physical stresses, stop destructive vibrations before they start, and squeeze out every last drop of efficiency, all while avoiding things like surge or stall, which are basically aerodynamic hiccups that can destroy an engine in a split second.
So the next time you flip a light switch or see a plane streaking across the sky, just remember this hidden giant. It really is a testament to human ingenuity, a symphony of thousands of parts, all spinning together in this perfect, violent harmony. It's a reminder that sometimes the most powerful forces that shape our world are the ones we never even see.